that when we go to an integral, and like we said, the integral of ln of x is 1 over x, but when we do the antiderivative, remember there was one little piece to it. Yeah, it actually turns out we can do a little better with this than just saying it's ln of x. It's actually the ln of absolute value of x, yes. What that opens up is that opens up more x's. We don't have to limit ourselves to just positive because on positive x's, because when you're doing logarithms, you do the logarithms for the real numbers. You do the logarithms of a positive number only, right? But if we've got the absolute value of x, that opens up x's to be positive or negatives. And we saw it did work out that way last time. I think that was the last thing I was able to do there. Okay? So don't forget, yeah, when you do the antiderivative, don't forget about your absolute values. It is the natural log of the absolute value of x when you have that scenario there. Okay. So let's utilize that to do some others. What if I had this integral? The integral of 4x over x squared plus 6 dx. Well, in some ways I guess it looks like the previous one we were talking about, but it's a lot more complicated looking, isn't it? Now, we'll be learning a lot of different techniques to integration. A lot of them. I'll give you that. Definitely we'll be learning a lot of integration. Guess what we should always start with looking for whenever we go to integrate something? Anybody see what we're going to do here to integrate this? My general rule of thumb, of course, if it's not just a direct, yeah, this 1 over x is, if it's not just something direct, like, always look to use U-Substitution in your next line of thinking there. We'll be learning all these techniques, but if you can use U-Substitution, that is by far going to be the easiest way to go. And this one is the U-Substitution here, because here's what, if you notice, if you let u be that x squared plus 6, you see what's going to happen? Du then is 2x dx. And du over 2x is dx. Do you see why that's going to work out pretty well? That x is going to cancel with that x, isn't it? So I'm going to get the integral of 4x over u, and then du is du over 2x. Yeah, and so that's going to get rid of the extra x there. Of course, the 2 cancels too, but so I get the integral of 2 over u du. This is good, because now I know, what about that? That's now just a direct ln, isn't it? I've got, instead of 1 over x, I've got 2 over u, but that 1 over x just, it could be 4 or 5. That's just going to come along for the ride, isn't it? This is going to be 2, what? ln of absolute value of u plus c, right? With me? Now, if I go finish it out, of course, I got to do x's instead of u's, so x squared plus 6 is the next step there. And then the next step is this. Like we were saying, the absolute value of x, that gets me x is positive or negative. But if you'll notice here, are the absolute values really necessary? Why aren't they necessary? This is always going to be positive no matter what, isn't it? If you square an x and add 6 to it, that's going to be a positive, so there's never going to be a time when that's negative. So, is it wrong to have them in there? No. Is it better not to have them in there? Yes, in this case. So the ultimate final answer, I would say, is just ln of x squared plus 6. The absolute values are not necessary there. Okay? With me? Now, if that had been x squared minus 6, hey, leave them in there, right? But x squared plus 6 or x squared plus a number, that's always going to be positive. Or if it was x cubed plus 6, leave them in there. But if this is always going to be positive, then the absolute values aren't necessary. Okay. Any questions on that? All right. Okay. Here's another. Let's do a definite integral. What about the definite integral? 1 to 3, 5 over 3x minus 5 dx. Well, it's not a direct integral by any means, but guess what I can use? U-substitution. Do a little U-substitution here. What do you think U would want to be? 3x minus 5. U is 3x minus 5, so du is 3 dx, so du over 3 is my dx. And so that's going to work out to be the integral of 5 over u du over 3. Yeah, so again, the 5/3 is just kind of a constant, isn't it? Then you got your 1 over u du. Hey, yeah, that's, again, just a natural log, isn't it? So it's 5/3 the natural log of the absolute value of u. Now I want to evaluate this one actually from x is 3 to 1, so go back to the x here, so it's 5/3 the ln of 3x minus 5 from 1 to 3. Is this okay? Yeah, you can see here the absolute values are necessary because, well, not in the case of 3, because what do we get? We get 5/3 ln. If I plug in 3, I have the ln of 9 minus 5. I have the ln of absolute value 4. That's just going to be ln of 4. Over here, though, I'd have, with 1 in there, that's going to be the ln of 3 minus 5, which is negative 2. So I wind up with 5/3 ln of 4 minus 5/3 ln of 2. Which is a pretty good answer. But let me show you how to make this answer even shorter. I mean, you could do the decimal, but remind you of a couple of, factor out the 5/3 there. So I get the ln of 4 minus the ln of 2. What do you know about subtracting logarithms? Can't those be combined? It's 5/3 times the ln of 4 divided by 2. Those can be combined if they're 2 logs subtracted. You can combine them by dividing, right? If they were added, you multiply them. But here, so isn't that just 5/3 the ln of 2? So sometimes you may get this answer. Their answer in the back says that, and that's what they've done. They've done a little bit of simplifying by some properties of the logarithms. Don't forget those. With me? Is that okay? All right. Well, questions on that one? Okay. Let's talk about what's called logarithmic differentiation. Here's why we do this. I may run into, down the line, never know, I may run into something like this. If I run into a function, x to the square root of x, what's strange or different about this? I've got variable in the base, variable in the power. So which is it? Is it an exponential or is it a power? Polynomial power. Well, the answer is, I guess both, but it's neither one either, right? You can't use the power rule and you can't use the exponential rule here because It's both of them. Transcendental, sometimes, functions of what these called. So that's the thing. Here we've got the variable in the power and in the exponent and in the base. Well, we can get around it by doing what's called logarithmic differentiation. And by logarithmic differentiation, here's what that means. We're just going to, first of all, start off with taking the log of both sides, ln of both sides. Because what that'll do, if I take the ln of y, take the ln of x to the square root of x. What you have to utilize there then, the reason this helps me there, is what about that on the right side? Well, since it's a logarithm, what can I do with this power? Yeah, it can come out front there. This power in a logarithm can be brought in front. So I have the ln of y equals the square root of x times the ln of x. Hence, the problem is solved because now I don't have a variable in the power and in the base. I just have this. Okay, that stuff I can do derivative of. The only problem is this side is now no longer just y, it's ln of y. So I have to do a little bit of implicit differentiation. Let's do the implicit differentiation here. You know what I mean? d dx both sides. If I d dx that, what do I get? Well, it's a logarithm, so I have to do the derivative of the logarithm. ln, so it's just 1 over y, isn't it? But since I'm doing the derivative with respect to x, what else do I need? dy dx. So this side, the d dx of it would be 1 over y times dy dx. Okay? The other side, well, it's not too bad, but it is a product rule. So do our product rule here. Square root of x times the derivative of that. Well, the derivative of ln of x is 1 over x. Plus the ln of x times the derivative of x to the 1/2, isn't it? So that would be 1/2 x to the minus 1/2. Cleaning it up a little bit, what I have here, what is this? Can I combine those? What's that? Simplify that. X to the minus 1/2. Yeah, because that's x to the first, that's x to the half, so it'd be 1/2 minus 1 there. So you with me? X to the minus 1/2 be there. And then this, well, there's not much there to do, but let's just write it this way. I guess we could factor off the x minus 1/2, but let's just, I don't think I did, so let's just leave it there. Now, what are we trying to find? We're trying to find y prime, the derivative. So I still have a little bit of work here to do. I need to solve for dy dx, so I need to multiply both sides by y. So my dy dx is going to be equal to y times x to the minus 1/2 plus 1/2 x to the minus 1/2 ln of x. Right? And then to get it explicitly in terms of x, change back the y. What is y equal? X to the square root of x. So the final derivative dy dx or y prime is x to the square root of x times x to the minus 1/2 plus 1/2 x to the minus 1/2 ln of x. How about that? I think I have another one. It's up to you. I don't think it'll clean it up just a whole lot. But yeah, if you wanted to factor off the x to minus 1/2 and write it as a separate factor, sure, go ahead. It'll stay in there, but all right. So sine of x. Let's do this one. y equals sine of x to the ln of x. I guess that one isn't as simple as the other one, but it's still not that bad. I mean, it doesn't look that bad, but still, you've got the base, x, and then you got x is in the base and x is in the power, so yeah. Transcendental, what they call those. So, to get the derivative of that, like I said, logarithmic differentiation. So what was that first step? ln both sides. And then that'll get that power out of there. So it'll be ln of y equals ln of x times ln of sine of x. d dx both sides. So that this will stay basically the same or be the same every time, won't it? The d dx of that, what is the d dx of that? 1 over y dy dx, or y prime, whatever you want to write there. And then over here, it'll be product rule. First times the derivative of the second, second times the derivative of the first. So what have I got? ln of x times derivative of that. Well, it'll be 1 over sine of x, right? With me? Times what? Cosine of x, yeah. The derivative of ln is 1 over that. And then the derivative of the inside is cosine. Plus, second, by my way anyway, ln of sine of x plus the derivative of ln of x. Well, that's easier. That's just 1 over x. One thing about cleaning this up, we can combine those. We could write them as one fraction. It'd be cosine over sine, and then we can write cosine over sine, cotangent. Yeah. So this is ln of x times cotangent of x, and there's nothing much there. Just ln of sine of x over x. That's what it comes out there to be. Now, again, you multiply both sides by y, so we get dy dx is y times all of that, right? And then just change over the y to sine of x to ln of x. You got it. Nothing to it. So this little thing, its derivative is that big long thing. Okay. Okay? All right? Questions or concerns?